So this video, we're going to talk about how to find an area of polar curves. The main question is this. If you have a polar curve described by r of theta, where theta is in between two angles, alpha and beta, what is the area enclosed? So here's a little picture. The polar curve is r of theta. It goes from angle alpha to angle beta. So I'd like to solve this problem, but first, before we get there, I want to remind you of areas under curves. We're going to adapt the same argument that we did in Calculus 1 to find areas under curves. So here was the idea from back then. You have an interval from A to B and a function on that interval. So here's a function f of x. To find the area under the curve, the idea was to chop up the interval from A to B into lots of little pieces. So you get a machete, chop, 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 slice the interval from A to B into lots of little pieces. So call this number A x0. This next number I slice at past A, x1. The next number, x2. And I chop everything up until I get to the last number, b, which I'll call xn. So anyway, you slice up the interval from A to B into lots of pieces, and then you draw rectangles approximating the area. So you draw a rectangle from the first interval, a rectangle on the second interval, a rectangle on every interval, and then you approximate the area under the curve by adding up the area in the rectangles. So the area is approximately equal to the height of the first rectangle. The height of the first rectangle is the function height at x1, so f of x1, times the width of the first rectangle, which would be x1 minus x0. The next rectangle you would add up would be f of x2 times x2 minus x1. And you keep adding up the areas of all the rectangles until you get to the last rectangle. So add everything up until you get to f of xn, which is f of b, times xn minus xn minus 1. And that's the approximate area because I'm just getting an approximation. You could see I'm off a little bit because the rectangles don't perfectly match the area. However, you can take a limit and get an exact answer. So taking the limit gives the exact area, no longer an approximation, but an exact area is equal to the integral from A to B of f of x dx. So when you take the limit as the number of slices gets larger and larger and larger, the definition is you get an integral as a result. So that was a very quick, brief recap of how to find areas under a curve based on our experience in Calculus 1. Now, I'm going to do the same idea except in polar. So what is this? In polar, let me draw a bigger depiction of what I have over here. So in polar, here's the situation. I again have a function, but it's in polar equations. I have a start angle alpha. So let's say this is my start angle alpha. So there's alpha. And I have an end angle beta. So beta's up here maybe. So that angle is beta. And I have a polar curve that kind of goes like this maybe. There's my polar equation. r is some function of theta. So I'll just put r of theta. Okay, so instead of slicing the x-axis as we did in the Calculus 1 type problem, I'm going to slice up according to angles. So I'm going to take angles theta 1, theta 2, up to theta n, just like we did here, except instead of slicing up the x-axis, I'm going to slice up different angles. So here is maybe my first angle, there's my second angle, there's my third angle. You know, I'm going to keep adding up angles. So this first angle I'll call theta 1, my second angle theta 2, my third angle going from the x-axis rotating up, that would be theta 3, and so that would be theta 3, and so on. And you keep slicing up the angles until you have n different angles. Let me draw one more maybe. Okay, then maybe I'll do this in pen because my picture's getting a little messy here. Then, instead of approximating the area with rectangles, I'm going to approximate the area with pi wedges. So I'm going to approximate the area of this first wedge by drawing. So I'm going to approximate with not rectangles, but with pi wedges. Maybe you can call these polar rectangles if you want. So I'm going to approximate with shapes that look like this. So a very thin piece of pizza. This is part of a circle. So this is part of a circle. It's just a wedge and part of a circle. It's like the last piece of pizza that no one wants to take to be polite, but it's the smallest piece. Okay, so the first pi wedge that I'm going to use looks like this. And then once I get to the, actually I'm going to go here. Once I get to the edge of the function, I'm going to continue and draw the piece of a circle. So there's my first pi wedge. My second pi wedge goes like this. This pi wedge here goes like that. This next one would go all the way out to here, and so on. So the area in the red wedges is approximately the area that I'd like in my polar curve. Now, so the area is approximately what? Well, if you understand circles a little bit, let's say the circle has radius r. So this is part of a circle. This circle has radius r. And let's say the amount of this circle is radian angle theta. The area of this pi wedge is given by 1/2 r squared theta. Now, if you're not comfortable with areas of circles, you could double check that this is the correct formula, because notice when theta is 2 pi, I have an entire circle, and the area is 1/2 r squared times 2 pi, which is the well-known formula pi r squared. So you could at least verify, if you don't know this fact about circles, that it's true in the case when I have 2 pi. Okay, so back to this problem. The area is approximately the radius of the first wedge. The radius of the first wedge is r theta 1. So r theta 1. So the area of the first wedge is 1/2 r theta 1 squared times the angle here, which would be theta 1 minus theta 0. That was the area of, maybe I'll shade it in to hopefully make it more clear. That's the area of this first pi wedge. The area of the second pi wedge would be 1/2 r theta 2 squared. That's the radius of the second pi wedge times the angle of the second pi wedge. The angle of the second pi wedge is theta 1 minus theta 2 minus theta 1. That was the area of the second piece. Anyway, you can keep adding things up till you get to the area of the last pi wedge, which would be 1/2 r theta n squared, theta n minus 1. Can you see the parallel between what we have here and what we have here? That's the approximate area. If I take the limit as the number of slices goes to infinity, we find the actual area. The actual area is an integral from my starting to my ending angles, alpha, beta, and then I have the exact same thing I had here. The only difference is my function f of x is now 1/2 r squared. So I get 1/2 r of theta squared. And instead of x's, I have thetas. So I have d theta. So this is the answer I was hoping to get to. This tells me the area enclosed by my polar curve. So join me in future videos to see examples of this in action.